Still waiting for the other. Okay, there's three other people who are not here. I don't know what your plans are, so I'll just go ahead and start. So the what Bill asked me to do is to do a primer or review, depending on your background, on well log information. So the type of data you're going to be using in this class are two very basic types. Speaking basically, you're going to be using seismic reflection data, okay, 2D and 3D, but mainly 3D. So that's seismic data, so that's data recorded, amplitudes recorded as a function of travel time. That's going to give you your sort of structural and stratigraphic view. Okay, so that's going to give geometry in a big way. The other type of data is well log data, which is at a particular place. So it's not 3D, it's just 1D data, so to speak. So those are the two different types of data, well log data and seismic reflection data. So what he'll ask me to do to begin with is to talk about well log data or borehole geophysical information. Okay, so obviously boreholes are going to give you information in just one place that you're going to use to extrapolate or interpolate through your seismic volume and try to give some sort of rock meaning to what are just, in other words, amplitudes and travel times from your seismic data. Okay, so this will be reviewed for some, it may be new for some others. So let's just be pretty informal about it. If you have questions or comments, I may ask you for some of the answers and some of the examples I showed. Just jump in, okay? So this is just a picture from actually the drilling site in Decatur, Illinois, where your first data set was collected, just to show that it's actually a site that has real data. And first things first, as far as a textbook, there's no textbook that you need to buy for this, but one thing that you might consider doing is getting basic well log analysis for geologists, published by AAPG. It's kind of old, 2004, but it's still a good book. It's actually used by the AAPG, American Association of Petroleum Geologists, for their course. So if you take one of their courses that lasts 4 or 5 days and is very expensive, that's the book you will use. And it's available online for free. So you can buy it if you want. I don't know what the list price is anymore, $50, $60. So if you want to have a book, you can do that. If you're a member of AAPG, you can get it fairly cheaply. But what I recommend is that you use online resources. As far as online resources go, these are just some things I put up here. They're actually live links. So when I give you the PowerPoint, I'll make this available to you. You can just click on one of these and it'll take you to a glossary or a site where you can look up information. So if we use a word like gamma ray log or neutron porosity log, whatever, then words that don't necessarily mean anything, matrix condition. You can dolomite. You can look those words up in one of these glossaries if it's unfamiliar to you. But as far as where you go to get this book, this is where some of you already know this, but you go to the library site, the Harold B. Lee Library, go to databases, and actually just copy it from here once I give this to you. But you go to library databases, and then type in AAPG just for a search item, then it'll take you to this thing here. So this is something that you can use to search for literature online. I think the library pays $400 or $500 per year for it. If you were a commercial entity, you'd be paying, I don't know, last time I checked several years ago, it was $20,000 a year. So this is a very nice resource. You can get a lot of stuff for free. It's licensed, it's not really free, but it's there for your use. The way you can search on this book is you type in this name, Krygowski. So if you want to write it down right now, Krygowski, Krygowski, one of the authors. It's a rather unique name. So if you search on that name, then you'll see the various chapters. You can download those for free. You don't have to buy the book, and a very nice high quality PDF. So what I suggest you do is not read the entire book. It's not really an assignment, but if you want to have some background information on some of the things I'm talking about, which would be the introductory chapter. It's always a good place to start. Called Introduction or Interpretation. And then there'll be a chapter on gamma ray logs, which I'll describe here a little bit, and also porosity logs. Those are the two types of logs that are mainly used, that and electrical resistivity, those three types of logs that are used in this study site in Decatur, Illinois. Okay. Some of you already have this. So what we're trying to do for the next 2 weeks is to give you a quick working knowledge of how open hole logs work. It's not to make you really necessarily a great expert. We had actually a class for that, but just so you know what we're talking about when we put something up on the screen, okay? So it'll motivate making sense out of the logs we're going to be using in the class that we're going to tie to the 3D seismic data volumes, okay? As I said, we have a separate grad class, Geology 521, that's dedicated towards understanding geophysical logs. What I'm giving you here is just a very quick and shaved down version of what usually takes a whole semester to do. This particular class, Geology 576, isn't replacing 521, but we decided to combine the two together for this particular semester. Okay, so what I thought I'd do is, since most of us are here, do some introductions. I don't think we did that last time, or if we did, let's do it again. But my name is John McBride. My background is in geophysics, all different types of geophysics, not just petroleum, so I do a lot of high resolution work, apply different waveform techniques to different environments, everything from glaciers to shallow faults. Do a lot of petroleum applications, particularly carbon sequestration applications, which this data set in Decatur is actually involved with. So that's me. I've worked for a couple of oil companies in the dim dark past, worked in different academic institutions, so I have a fairly broad, or at least fractured background. So, Alex, you want to talk a little bit about yourself, but keep it under 45 minutes. Maybe what your thesis is, why you're here, whatever you want to say.
Sure. My name is Alex. I graduated geology from Texas Tech University for my bachelor's. And then when I came up here, I'm working with Dr. Hudson. We're doing a project on stratigraphy and source rock characterization. And we're also going to do some isotope geochronology. That's kind of like a groundbreaking new thing with black shales. I'm going to get into oil and gas. I like mountain biking.
That's great. So unconventional resources.
Well, most of what they do in my thesis is conventional.
But you'll be looking at shales, production for shales.
Yeah, they're trying to develop a higher stratigraphic model, resolution model for so that they can understand generation and migration of hydrocarbons.
Yeah. So, okay, great. Yeah.
My name is Naif. I'm from Indonesia. This is my second semester at GeoU. I'm working with Dr. Harris. We're doing research in coastal uplift and tsunami conflicts.
Great, thank you. Hey?
I'm May. I'm from Taiwan. I work with Dr. Harris. And so my research is about tsunami in West Java. Yeah, that's it.
Okay. Guys want to go?
Yeah.
Good?
So I'm Raleigh. I'm a grad student in the civil engineering department. I'm working with Dr. Guthrie, Spencer Guthrie, and we're looking at how reinforcing road-based materials can be achieved through using a product called Geol and how effective it is. It's basically like a plastic polymer mesh that you can lay on in the road, in the aggregate-based material, and it will help to reinforce it. So let's say I should be done in April, and I'm interested in oil and gas.
Okay. Great, thank you.
Yeah.
I'm Alex, and I'm an undergraduate civil engineering student. I am interested in oil and gas and reservoir. Specifically, I've worked in oil fields as a well gauger and also on doing facility engineering work for gas treatment. Really comes out of well. But I think I'd like to understand more about reservoirs and what's going on.
Okay, great. So if you have some insight, show something, make a comment, please. It's been a long time since I've been in an oil field.
Promise.
There's one other student, Ben Godwin. He's not here, but he's working with me actually on studying active faults along the Wasatch Hurricane Fault System. And, a lot of petroleum engineering people start off in civil engineering, as you probably know, and it's kind of hard to find petroleum engineering programs per se. There's not so many of them. There were more in the past, but what you typically have now, I think, at least in this country, is people will get a degree in civil or chemical or geology or whatever, and then they migrate into petroleum engineering, which in a way is more stable, because you're always going to be pumping oil, but you won't always be looking for it. So great to have you all here. I know it's a bit of a heterogeneous group, so again, you have a question or I say something like that doesn't make any sense, just please ask me. We can be pretty informal about it. And by the way, you can just call me John. That is actually my real name. Doctor or brother, I feel like it's too formal or I'm in trouble or something. Okay. So, type of logs we're going to talk about in the next couple of weeks that Bill asked me to cover. We're going to group them sort of by function, not by physics. So the very first type of log, and this kind of follows the order in which you actually read them from left to right. You read logs kind of like you read a sentence from left to right. So starting on the left, the types of logs you have are correlation or lithology logs. So you say, well, what type of material do I have? What type of rock is it? Is it a limestone, calcium carbonate? Is it sandstone, silicon dioxide? Is it a reservoir? Is it more of a seal? Is it a sink? You start reading that information on the left side under the category of correlation with lithology logs. The particular type of log we'll be dealing with is the highest resolution log in that category, gamma ray. We'll also make reference to ST or spontaneous potential, but it doesn't have such a wide application for what we're going to be doing in this class as gamma ray. Gamma ray is the best type of log for looking at bed boundaries, reservoir versus not reservoir, radioactive versus not radioactive, things like that. In the middle part of your log display is electrical resistivity. You often just use the word resistivity, but obviously we're talking about electrical resistivity. Two broad types, induction and lateral log. Induction logs are the more recent 1950s. It doesn't sound recent, but it's more recent than the electrode-based logs from 1920s. So electrical resistivity is telling you what you think. So it tells you something about the fluids, right? Because your matrix is probably going to have, with some very important exceptions, a very high resistivity. You could almost consider it infinite electrical resistivity in your matrix. So like if you had quartz, glass, well, that's an insulator, right? So it doesn't conduct, so it doesn't really contribute to the resistivity in the way we're looking for. So often electrical resistivity is telling you something about the fluids. And of course, you're most curious about whether it's oil or gas or salt water or fresh water. Whereas the lithology is telling you something about what type of rock you're looking at. And then lastly, porosity. How much do you have? So this is your framework, your matrix. Your middle part of your log is, well, what type of fluid do you have? And then the last category on the very rightmost part of the log is, well, how much? It's a storage parameter. So porosity, the types of logs we'll talk about are density and neutron, which are almost always used together, so sometimes called a density-neutron combination, but then also sonic or acoustic logs. So three different types of porosity logs. So this is what we'll be doing in the next couple of weeks. So first of all, what is well log analysis? This may be a little bit pedantic, but what you're trying to do is you're trying to connect physical properties that are of interest to a petroleum engineer or geologist. What are the physical properties of the rocks and the fluids? Now, geologists, a typical geologist doesn't work in petroleum. When he or she says rock, what he really is talking about, or she, is about the matrix. What is the solid part? Well, of course, if you're a petroleum engineer or a geologist, you're just not interested in the solid part. There's no money in that, right? When you say rock, you're talking about the matrix and the fluids. So when we say physical properties, we're not just talking about a rock. Okay, we're actually talking about the fluids as well. So we think of a rock in a little bit different way. It's the integrated system that we're talking about, the petrophysical parameters of the reservoir, which is both matrix and fluids. Okay, so things we might be interested in are Well, what type of porosity? Is it big or little porosity? What type of fluid? How much fluid? What's the fluid saturation? We don't worry about that so much in this class because we're just kind of look at geometries and lithologic environments and sedimentological environments, but eventually we're interested in the fluid saturation as well. So I'll use this word matrix. I've already done it. Matrix, what that means in this particular context is the solid or rock framework. So you think about a bunch of marbles. To bring in a glass of marbles, I guess. Marbles would be the actual rock framework. Most marbles are made out of glass, or silicon dioxide, or in the mineralogical form quartz. Okay, that's the matrix. So the solid framework. And then what's filling in the porosity? That's the fluid. So we talk about porosity and matrix. Okay, both are important. Matrix, the solid part, the porosity then could be filled just with air, which is also fluid, but more likely with oil or gas or water. Okay, I'll say this over and over again. It's very important to understand that your measurements are indirect. So you don't actually direct any type of quantity. You don't directly measure any type of quantity that you're interested in. So we talk about porosity logs all the time, but there actually is no such thing as a porosity log in the sense that you have a log that just immediately measures porosity. That doesn't happen. You measure a bunch of other things and you make a model of the porosity. It doesn't give you porosity. Initially, it gives you some other parameter like density of electrons or what's the density of hydrogen ions, not porosity. So you have to take that indirectness, use interpretation to get what you want. Very important to understand that. Otherwise, you'll just do the wrong answer. Just some terms for those that are not haven't had a lot of geology classes. When we say mineral, we're talking about a crystalline substance that has a fixed chemical composition. So when I say quartz, that means silicon dioxide. When I say calcite, what's that? Somebody help me out here.
Calcium carbonate.
So that's calcium carbonate. Same thing as chalk or Tums or whatever your favorite acid is. So that would be an example of a mineral. So typical type of minerals we might think about in well logs would be calcite, calcium carbonate, quartz, silicon dioxide, dolomite, calcium magnesium carbonate, and there's lots and lots of others, of course. But those are kind of your three that are very typical that help make up a reservoir matrix. Okay, so that's mineral. And a rock is an aggregate defined by minerals, but then their combination. What types of minerals do you have, and how are they arranged together, which we might call texture. So that's the difference between rock and a mineral. It's important to make this distinction because some well logs are kind of operating sort of at a molecular level or sub-even molecular interval. They're looking at interactions that are basically atomic level interactions. So that's really responding to the formation's mineralogy. Whereas other types of logs are more bulk. They're looking at just the very bulk property. A good example of that would be the sonic or acoustic porosity log, which is just looking at the travel time, the sonic or seismic travel time through an interval of rock. So that's looking at everything, right? It's not actually responding just particularly to the scattering pattern, say, of calcium sulfate. Okay, it's actually looking at the entire bulk. So we kind of make this distinction between rocks and minerals and keep that in mind as we go through the class. So the very first thing is, what is the environment that you encounter in the borehole? So the problem with well logging, the big paradox is that, well, you have all these rocks down here, they're minding their own business, rocks and their fluids. You drill a hole to get some information. Well, it's kind of like, I don't know, it's like an anthropologist going someplace and studying people. As soon as the anthropologist is there, he or she has changed the environment simply by interacting with people, right? Well, a well log is something similar. You make a hole in the rock and you completely change the environment. How do you change the environment of the rock by drilling a hole through it?
Fluids.
No, yeah, I think we were going to say the same thing. You drain some fluids, so that's a big part of it.
Fluids come out, fluids go in, right? So if you just think about the matrix, well, you don't change the matrix that much necessarily. You might. But of course, you change the fluid distribution in a huge way. So as soon as you drill a hole, you change the very thing that you're trying to detect. So it's very difficult. Again, it's like going in and exploring a people that you're trying to understand. But once you start interacting with them, they behave differently around you. So it's the same kind of thing with the borehole. This is a classic picture. I think this is from Schlumberger, showing your borehole environment. So you usually use the pictures like these if you're not already. So here's your borehole, and the different colors, different shades of blue represent what? Different types of invasion. So in other words, the fluid is under pressure, it encounters a porous and permeable zone, and so the first thing that happens, the fluid spurts into the formation, and you set up a distribution of different properties, depending on what we're talking about. So the properties could be stratified in terms of what? What's going to be the difference between here and here? Say, this is further into the formation, this is right next to the borehole. What would be different about here versus here?
The closer you get to the borehole, the more invasion from the fluids.
That we're actually started off with, right? So you have something called mud or drilling fluid, a little bit more fancy sounding, but mud in the hole. And so where it's have the flush zone means that you flushed what out? You flushed out the original fluids and you replaced it mainly, not entirely, but mainly with the fluids in your borehole, because the borehole's under pressure, right? And then as you get further into the formation, you eventually get into the uninvaded zone where you have the pristine fluids that were there before you actually started drilling into it, whether that's salt water or fresh water or oil or gas or whatever it might be. Okay, so the big paradox you have is that, well, you're going to be pulling up a drilling tool through the hole, measuring formation properties, but a lot of those properties are going to be influenced by what happens here in the first few inches or maybe foot within the formation. You're trying to get to these properties, but you have to see through these properties. See what I'm getting at? So it's a bit of a problem, because if you could drill a hole without having any invasion, well, then that would be good, but that's not going to happen. You're always going to have invasion of fluids. This is particularly important for the electrical resistivity tools, because if you're looking at a stratification in terms of original mud versus formation water, what physical property is going to vary? What physical property? The temperature, the concentration of what? Of, say, salinity. That's the bigger, right? Because you may be drilling with fresh water mud, or maybe it's oil-based mud, or diesel, okay? But you probably have salt water. Most of the water in the earth is salt. You get very deep into the earth, circulation of ions over time makes water salty. It's not drinkable. Most of it's not good for anything in terms of human use. So most of your water is going to be salt water at any particular depth beyond a certain level. So you're going to be looking at a stratification of fresh water versus salt water. What's that going to do to electrical resistivity? So if you have freshwater mud, you're spurting that into the formation. What does that do to electrical resistivity? Does it go up or down? Yeah, because you have less salt water. Whereas here you're retaining your original high salinity water, then you have low resistivity, right? So it's just high resistivity because it's fresh, low because it's salt, okay? So that's particularly a problem with your electrical resistivity logs, not so much with the other logs. If you have a log that's not really responding very much to the fluids, then this doesn't matter. But electrical resistivity responds more to the fluids than to the matrix, unless the matrix is conductive. Okay. So what would that look like? If we sort of take a cross-section through here and blow this up, we might see something like this. This is our borehole. This would be what's called a mud cape or filter cape. This is the mud filtrate that's just being filtered out as the mud is spurting into the formation. So it's just filtering out, and it actually forms a cake or layer, thin layer on the edge of the borehole, if you have a porous and permeable zone. So what you would have after that then, if you go deeper in the formation, so you get the idea, this is a cross-section, this is the borehole. Get a zone of bridging where you have particulate matter, because you're going to be drilling with mud. So what is that? It's clay particles. You may have barite in there. Other types of salts may be present. The stuff that's kind of particulate is going to be filtered out and form this bridging zone like you see here. Then you'll have the mud that's actually invaded just with the initial spurt, and then the uninvaded or uncontaminated. So this would be your stratification. Of course, this is probably going to be transitional. So this is even too simple. What this would look like if you did a cross-section parallel to the surface of the Earth is something like this. It's oversimplified, but you'd have a borehole here, right? That's where you drilled your hole. You have a zone of bridging that gradually is then replaced just by your mud spurt, and then you get into the uninvaded zone. And even this is way simplified. So what's the point again is that some logs have to see through all of these different zones, particularly electrical resistivity logs. So what that means with your electric resistivity logs is you see lots of them. You see an array of logs. You see at least 3 logs, one perhaps designed to look here, another looks a little bit deeper, and another deeper still. So electrical resistivity logs, which I'll show you here in a little bit, typically have at least 3 components. And sometimes you'll see 9 different logs run. If you have 9 different logs run, that means you're just looking at 9 different depths laterally into the formation. Okay. So what that would do eventually, after everything is equilibrated, is you might have 2 very basic types of cross-section developed. Something like this. So we have sand and shale. Now, somebody want to explain what shale is? Somebody help me out. Geologist's going to have to help me out.
It's like a mudstone. It's got a lot of clay and a lot of like potassium and radioactive elements, sort of like that. And, but it's also very high in organic material usually.
It could be, yeah. What about its mechanical properties?
Not porous.
It's weak, right? I mean, it could have a lot of porosity. Shales are typically very porous, but they have poor permeability. They don't have good permeability, but they're mechanically weak. If you think about something made out of clay, how strong is clay? Every engineer knows that clay is not very strong. You don't want to build a house on clay. Shales are largely composed of clay. So typically what you have, if you look at a cross-section, this is a drilling bit here for scale, through the boreholes, that's your shales that are dominated by clay mineralogy will actually open up and cave in so that your hole will get larger within a shale because they're mechanically weak. It just dissolves or falls apart. You drill through it, it's friable, it just falls apart because it's not very well cemented. Whereas the sandstone, what's the deal with the sandstone? You build up a filter cake or a mud cake, is shown here by the black. Why? Why would that build up? Because you're forcing mud into the formation, right? This is under pressure. You've got mud, you have water, you've got particulate matter, clay floating around there. The clay is filtered out as the water is pushed into the formation, right? But the clay is too big to actually follow the water. So the clay is left behind as kind of a scummy layer that forms what's called this mud cake. So a mud cake, if you see that the hole is constricted, that gives you an idea that you have a permeable formation. Because this will not happen if you're drilling through, say, solid steel for some strange reason. You have no porosity and permeability, you form no mud cake. That makes sense? This is a very basic kind of intuition about what's going to happen when you start drilling and how the geometry of the hole is going to change, okay? So you get typically washed out zones and shales. This would be shown by a caliper log, which we're not going to talk about explicitly, but you can imagine you're always going to have some type of log that's measuring the size of the hole. Where the hole is wider, it may suggest that you have a weak zone. Now, it could be something other than shale, but shale is a likely possibility. Whereas you'll have the mud cake build up in, say, a sandstone that's porous and permeable. Now, keep in mind that shales are typically porous. They can have a very high porosity, but the porosity is disordered. It's not connected. So there's no permeability or very poor permeability. That's why typically shales were considered a seal in a conventional reservoir, I add. Shales might be considered a seal, whereas a sandstone or a porous and permeable limestone would be considered a reservoir. Okay, so we talked about invasion. So here's just a little question. What determines the lateral length of invasion related to porosity? So let's say we have a very simple situation. We have mud circulating in a hole. It's under pressure. You have porosity, 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 different levels, and then shales that are forming as seals. So this would be a good diagram for an engineer because it says porosity with a certain amount, a seal of a certain thickness, and then more porosity. So the question is, where are you going to have your greatest invasion? Which one of these is invasion going to be great? Assuming that you have a finite amount of water drilling fluid that's going to invade, because it's going to shut off after a while. It just doesn't go on forever. It shuts off because it shuts itself off because it seals itself in. So what type of rocks do you have the greatest invasion? Making these assumptions.
Are we also to assume that the pressure is the same
Yeah.
throughout the mud?
Yeah, everything's the same. So where's your invasion going to be higher? In high porosity rocks or low porosity? Assuming that they're permeable and the same thickness. So it's kind of a setup question. So high porosity, you're going to have high invasion. So think that through. Again, you have a finite amount of fluid that's going to go in, right? So if I have a finite amount of fluid that's going to go into 10%, let's say, I don't know, we can actually do a problem with it. Let's say it has 40 gallons. It's going to go into here. I have to distribute 40 gallons. How far is it going to go? Well, let's say it goes here. I have 40 gallons that's going to go on here. Where is that going to go? Well, I have more room, right? So maybe it only goes this far. So this is like a bigger room versus a smaller room. So what your distribution would look like is that. So you have much greater invasion when you have low porosity rocks, given the equal amounts of fluid and similar properties in terms of permeability. So again, why is this important? Because this is going to affect your fluid distribution, and it's going to influence the way your resistivity logs look. Because if I have a resistivity log or an array of logs, one that looks here, another that looks here, and another that looks here, well, two of the logs might look the same because the fluid invasion is the same. That is, there's none. Whereas if I look over here, where I have lots of invasion, well, maybe the logs look a little bit different if I'm comparing here versus here. That makes sense? So it depends where you're looking with your logs. So you have to understand invasion to understand resistivity logs. That's the problem. Right. So that's the borehole environment. What about the drilling environment? Here's a picture I took at a drilling site near Rock Springs several years ago. Lots of things we could talk about, but what I want to talk about here is the point at which you actually say is zero. So where is zero depth? It's non-trivial. There are actually three possibilities for zero depth for log. It's very important because you're going to tie that log to your seismic data. The seismic data is going to have a datum. Everything has a datum, right? Is it ground level? Is it sea level? Is it some arbitrary number, 300 feet above sea level? You have to know that. And once you decide where your datum is on your seismic data, then you have to decide, well, I have a log, but where does it start? You might think that's a trivial question, but where does it start? You tell me, what are your possibilities? So where's this guy standing?
Ground level.
Well, it's a ground, is it?
Probably on the platform.
I don't show you enough to actually answer the question, but you can be sure it's not at ground level, right? So this is the derrick floor, or drilling floor, okay? So you might actually see some notes that say DL on the log, which stands for drilling floor, okay? What's another possibility? So it's not ground level, so ground level is another possibility, right? So maybe your datum for your log is ground level. What's another possibility? We got drilling floor, we got ground level, we got one more.
The bottom of the hole, maybe?
Well, the bottom of the hole is TD, that's total depth, but in terms of where we say zero is, one possibility would be called the Kelly bushing. Now, not to get into drilling technology too much here, but the bushing on the Kelly pipe is attached to your drill stem, shown here on this simple cartoon. Where you attach the Kelly pipe, which is up above, it transfers motion from your drawworks to your drilling, because you're drilling, you turn the bit, right? So it's always turning. That's what's going on here. The top of the Kelly bushing, we need for that to happen. How do you make this get smaller? Okay. Well, the top of the Kelly bushing could also be a place where you have drilling, where you actually have your measurement.
So you take 2 fingers and slide out.
So I'll slide out. Maybe I don't have any.
Magic.
I'm not alive, actually.
Do you want me to Nancy?
Yeah. Okay, great. Okay. So what I'm talking about is where you make your measurement. So it's very important. So drilling floor, or drilling level, drilling floor, DF, DL, the Kelly bushing, the top of that, which is only going to be about this far above your drilling floor, right? And then ground level.
Can you show where is the drilling pushing on the cartoon?
On that last picture, see if I can go back. Can I do this? So that's the Kelly bushing.
And where is it on the cartoon?
Oh, it'd be right there.
Number 8?
Yeah, well, 8 is actually referring to the rotary table, which is this thing with the Kelly bushing is just above the rotary table.
Oh.
It's not actually shown here very well, but it'd be right there. Okay. Oops.
Okay.
Okay. But the explanation of number 10 is actually Kelly.
Yeah, Kelly is the Kelly pipe. So what 10 refers to is the Kelly pipe. Yeah. There's lots of parts. We didn't want to get into all the parts here, but this is the Kelly pipe, the Kelly bushing, this thing that's kind of reddish, the turntable with the rotary table. This turntable goes with the photograph. That's this thing right here. This is the derrick floor, or drill floor that we're standing on. That's where he's standing. It doesn't actually show a Kelly bushing on this particular picture right here. That's why I have that one. So why is it important? I'm not interested in you knowing all the different parts of a drill rig, okay? That's not what we're about. But it's important because if you look at a log, it'll actually refer to those different locations. So first of all, this is from a paper copy, but this will be in your header. We'll be using digital data, but all the same type of data is there. It's basically a legal document. It's all got to be correct. It's extremely important. Where it will give you a location, the elevation. You've got to know what elevation we're talking about. Of course, that's what type of tools were used, and also what type of parameters that were in existence for your conditions, logging. So, for example, temperature. That's important. Okay, temperature is important. What else might be important? What's a parameter that's based on uniquely to the drill site that might be important? We got elevation, we got location, what's some other things? Temperature, because resistivity changes with temperature, so you got to know temperature. What else is important? You have drilling mud, right? So that's great. You start off with a known resistivity fluid, right? So you know what that resistivity is to begin with because you can measure it, and you can measure it as a function of temperature, right? So you start off with everything completely known. That fluid is going to be pushed into or invading the formation. So you start off with something known. So you know what your drilling fluid is. So all that information is here. Very important to have all that. Okay, now this has got a lot more information than we want to dwell on right now. But for example, RMF, RM stands for resistivity of the mud. RMF stands for resistivity of the mud filtrate. And it's going to be given in ohm meters, usual units for resistivity, and will be a function of temperature. So when you give a resistivity measurement, you also say at what temperature. If you don't say at what temperature, then it's pretty meaningless. Okay, you don't know so much about it. But here is again, see ground level is your permanent datum. KB is Kelly bushing, saying that it's 11 feet above the permanent datum. And here are your different variations of elevation. Kelly bushing, this one, highlighted here. Kelly bushing is 1,119. Drilling floor, 1,120, because the Kelly bushing is only about this high, right? And then ground level, of course, is beneath all of that, 1,108. So not a huge amount of difference, but how thick is a reservoir these days? How thick? Now, if it's like 1912, it's got to be a pretty big reservoir to be of value. But think about the price of oil if it were, what was it a few years ago, $120 a barrel? So a reservoir that's this thick could actually make a lot of money. But how much is this? This is what, 5 feet? What is that, 4 feet? So a few feet can make a difference. See what I'm getting at? A few feet can make a difference. Therefore, it's important to make a distinction. Okay. So other information, like I said, information about the type of fluid used. And then just so you know, what you would expect to see is if you ran, say, a gamma ray tool or an acoustic log or density log, then you need to know the parameters that pertain to the value that you're trying to get out of that log. So, for example, the density porosity log, well, what were your assumptions about the matrix density, for example? I'll explain that in a little bit, but all that information is here. So this isn't something like just the fine print on the back of the cereal box that's just there for legal reasons and nothing else. You actually use this information if you're going to get any kind of detailed information. Now, if you're just trying to match squiggles up together, that's maybe not so important. But if you're trying to get any type of petrophysical information, you got to have all this stuff. Okay. So, so here, finally, a well log. So well logs are something that's been around. I guess the first well log is like 1920 something. And since that time, even though you've got a huge amount of different companies doing well log analysis, the competition is huge, right? The oil commodity is something that's pretty fierce. Not a lot of friendly cooperation in the oil business, except in this case of how logs are displayed. Despite all the competition and all the variation that's gone on over the past decades, well logs can have a similar format, not depending on any type of company. It's fairly consistent. So let's just talk about well logs a little bit just to get used to it. This is called an API standard. API stands for American Petroleum Institute. So a fairly standard display where you have seen several tracks. So track 1 would be that lithology column that I talked about a few slides ago. So in this particular case, it's showing a gamma ray log, which I'll talk about in a little bit, in the blue dashed line. Okay, so that is your lithology track. Of course, you have a depth track, which is actually recorded as a function of time and then later converted to depth. But there's your depth track, right, in feet usually in this country. And then what's your middle one? Track 2, the electrical resistivity. So this is giving you information about the matrix, mainly, if you're looking at gamma ray logs. This is giving you information about the fluid, mainly, always with exception, unless you have low resistivities within your matrix, but usually you don't. Okay, so information about the fluid's electrical resistivity, and then track 3 is porosity.
Are they always track 1, 2, and 3, or is that just the configuration of this card?
This is fairly typical. Now sometimes, it depends how you're looking at logs. If you have an old paper copy, sometimes they will put one on one, one on the other. But the most typical displays, they have 3 tracks and then a depth track. Okay, so that you can read it from left to right. So again, lithology or matrix dominated, fluid dominated effect, and then storage. How much storage you have, how much porosity you have. This is going from minus 15%, we'll explain that a little bit, to 45%. Now why do you have this is that you have different types of signatures based on whether you have a reservoir or not a reservoir. So you want to be able to read this, take advantage of pattern recognition, because you'll have lots of different types of logs. This is actually a fairly parsimonious display. Other displays might have 9 different types of electrical resistivity logs. Over on the porosity track, you might have 6 different logs. It can be a real mess. You want to be able to display them in such a way that you get pattern recognition working for you. Okay, so typically, we'll explain this as we go along. You need to get used to the idea as you have a kick or deflection to the left, that's suggesting a reservoir. We'll explain why that is. High porosities are usually shown, or always shown, as moving to the right. So on the right is high porosity. And then with your resistivity logs, well, you would expect if you have low resistivity, what type of fluid do you have if it's low resistivity or high conductivity? So you have highly conductive or low resistivity. What type of fluid is it? Salt water, right? Or water, but you know, at this particular depth, 14,000 feet more, that's going to be salt water. So as it moves to lower resistivities, that's going to be wet, right? And in pay zones, well, what's oil? Oil is high resistivity or low resistivity? Higher, right? It's more. What would you rather fall into if you're going to be in a lightning storm? Well, a pot of oil rather than water. Oil is not a conductor. It's resistive, so your pay would be kicking to the left, whereas, or to the right, excuse me, whereas your wet zones kicking to the left, right? So you get this pattern in your mind where you have something like a Christmas tree, right? Which is kind of a good analogy. You have these type of pattern here. This typically might suggest that you have a pay zone. But of course, you also want to look for high porosity as well. So again, the whole idea is patterns. It takes a long time to get used to the patterns, but one of the objectives is to get you comfortable with the displays. Okay. So as far as reading logs, you might have noticed on that last slide that you had both linear and log displays. Okay, logarithmic and linear displays. Now, why would you have a logarithmic display? Why would you ever have that? What's the purpose of having a logarithmic display? Why do you do that in general?
Make it more readable.
Right.
So you don't have to look way out.
Right, but if I'm just say counting from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, those are my choices. Well, I don't need a log display, right? Because it's just 2 orders of magnitude, or maybe just 1. You'll have a logarithmic display when you have a great variation in order of magnitude. Resistivity, electrical resistivity can vary by huge order of magnitudes, okay? Whereas other parameters are linear, they don't have a big range in terms of numbers. So just how many numbers you have. So this is a typical display showing electrical resistivity here, and then let's say gamma ray shown in the solid line here. Gamma ray is linear, this is log. Now, you have to get used to these types of displays. People will mess these up sometimes. This is 0.2, all right? And then this 10 to the 0, 10 to the 1, 2, etc. So 10 to the 0 is obviously just 1, right? So you have 1, 100, 1, 10, 100, 1,000. So you need to get used to these types of displays. This particular case, you're going from 2,000, in this case all meters, to 0.2. Of course, there's no 0. Every once in a while, somebody will talk about 0 resistivity. Well, you can't display 0 on a log display, obviously. Okay? So you need to get used to these types of displays. Some are linear and some are log. Okay? So we just have some examples here. Right? So so far we talked about the borehole environment, the drilling environment. Let's get into the actual well logs now. So the first type is a gamma ray log. It's a lithology log. It's used for correlation. When I say correlation, what does that mean? Can somebody help me out here? Correlation of what? Well, what are we correlating? I have a well here. I have another well, and another, and another, and another, right? I'm trying to track a reservoir around my oil field. So we call that correlation of the reservoir. So rock correlation. So your gamma ray logs would be used for correlation because particular formations that are of interest, a reservoir or a shale, might have a particular signature, and you use the expression of the gamma ray log to find that signature in different places. The other type of lithology log, which is referred to very briefly, is SP or spontaneous potential. Not as important for our study, mainly using the higher resolution gamma ray log. Okay, so let's just do a review, or if you haven't had this before, it'll be a primer. This is the picture I took. Looking at log tools is sort of boring because they're always armored. They all tend to look the same once you look at it very carefully, but this is a gamma ray tool on the right here, just to give you an idea of what we're looking at. Okay, so gamma ray is what type of tool? We got 2 choices, passive or active. When I say passive or active, what am I talking about?
Whether it affects the rock.
Yeah, are you doing something to the thing you're trying to study, or are you just sort of watching it or listening to it or measuring something about it, right? So passive is you're not doing anything to it. You're just measuring something. You're looking at it. Active means you're doing something to it and then looking at the response. Okay. So natural gamma ray is a passive tool, and in a very simple way of thinking, what you're looking at is natural gamma radiation that's emitted by the formation. And typically what you might expect is that shales have a high gamma radiation. We'll talk about why. Whereas other rocks maybe have a low amount of radiation. So sometimes we talk about these as dirty versus clean. So a dirty formation has high gamma radiation, and clean formation has low radiation. And it's important to make that distinction. So when you talk about gamma radiation, what are the typical natural sources? Potassium, uranium, and thorium. Okay. So that just should become natural to remember those, potassium being the most important one. Why do we care? Because shales are made up of clays, and as Alex Washburn here already said, shales have a high concentration of potassium. What type of mineral would you find potassium in? Those are the geologists. Clay minerals, but there's something called feldspar. I don't have an example with me, but I have some pictures. But they're a typical component of shale. So shales have a lot of this in it, have a lot of potassium in them. So shales will typically have a very high value for gamma radiation. Okay, so that's important to remember. Shales show high gamma radiation, but notice have a low deflection. So deflection from what? Deflection from our maximum value, which we typically call in the oil business a shale baseline. The shales typically have the highest gamma radiation, usually. So we would call this a shale baseline because, again, shales have the highest. Whereas a formation that's of interest as a reservoir may have a fairly low value for gamma radiation. And notice that we don't call it a sandstone. We don't call it anything. We just simply say it's not a shale. Okay. So a generalization that's kind of dangerous, like a lot of generalizations, that trapeze zones typically would have lower gamma radiation. Why? Because what makes a very good reservoir? A jar of marbles, right? Think about marbles stacked together. Oil can flow through it. The marbles form a nice matrix for the reservoir. How much of these elements do you have in marbles? Marbles being made out of glass or quartz. Well, see, silicon dioxide, so there's none of that, none of these and that, right? Make sense? Okay, so if you think in terms of a conventional reservoir is going to be made out of calcium carbonate or calcium magnesium carbonate or silicon dioxide. None of these elements are present in those typical conventional reservoirs. So you expect conventional reservoirs to be fairly low in gamma radiation. That's why the gamma ray tool is so important, because it gives you a first pass. Where might you expect to have a conventional reservoir? Okay. So the gotcha, though, is that it doesn't always tell you what the lithology is. You have to know the context. If you're drilling in a place like the Gulf of Mexico, well, you have sand and shale, sandy quartz and shale. That's pretty much all you have, occasional marls or carbonates. But in that type of context, then you might look at your pay zone and say that's probably quartz. And you look at your hot zones and say that's probably shale. Well, what if you're drilling someplace like the Williston Basin, for example, that has a lot of calcium carbonates or calcium magnesium carbonates? Well, then gamma ray doesn't actually answer that question very well. So just to remind ourselves, there's something I just pulled off the internet showing wavelength, getting smaller wavelengths going up, higher frequencies going up. Gamma radiation is here. Why is gamma radiation make such a good tool? Okay, so they're not the same as some type of particle. I mean, I'm not a nuclear physicist. I know as much about Homer Simpson, I guess, not much more than that. But what makes them so useful as a tool? Gamma radiation. Well, what is it about gamma radiation that makes it a good tool for studying a rock formation? What? Well, if you're just listening, so to speak, or recording, yeah, you don't have to do anything to it. So, gamma radiation is free, yes.
Gamma rays are really, really tiny.
At a very, very small wavelength, right? So they can penetrate at high energy. So they can penetrate drill pipe. They can penetrate fairly deeply into or out of a formation. So that's why one of the reasons why gamma radiation works so well. Also, it's not electrically charged, so it's not being influenced by particles in the natural formation that have a charge. Okay, which some of them are. Okay, so gamma radiation is very, very useful tool. Potassium is your principal component for natural radiation. The type of rocks we're talking about. Now, obviously, uranium is big as well, but we're not usually looking for uranium. So your typical types of rocks are clay minerals. So I just picked one out, montmorillonite. Quite familiar if you've had a class in engineering geology. Lots of different types of clay minerals, smectite, illite, montmorillonite, lots and lots of different types. Most of them are rich in potassium. So the elements of the rock types, mineral types that make up a shale, high potassium. Okay, feldspar is just another mineral term that has a high potassium content. Okay, so what's the point? Is that shales have a lot of these types of minerals in them. Therefore, they have a lot of potassium. Therefore, they have a high gamma ray. Therefore, the gamma ray is showing not so deflective. Because deflection means deflection towards the low numbers. So, what are they good for? Well, lots of things for correlation, because as you'll see, different formations will have different gamma signatures. And in fact, if you had a spectral gamma ray tool, then you can actually look at the proportion of potassium, thorium, or uranium within the formation. So spectral gamma ray tools will actually divide this up. But the basic applications of that correlation, where do you draw your bed boundary? Okay, so how thick is the formation? Your gamma ray tool is going to tell you how thick something is. Where do you draw your bed boundary? And overall, if you have a well log that's say 10,000 feet, and you have shale, sand, shale, sand, shale, sand, or shale and not shale, well, it's going to give you the volume of shale. Okay. So just some typical parameters. I sometimes show these. This is just a Schlumberger rig actually operating in a soybean field in Illinois doing gamma radiation. Again, the advantage of the gamma ray tool, it can be run under any conditions. Not so with all the tools. So it can be open hole, it can be cased hole, it can be centered, it could be pushed up against the side of the borehole, and then the fluid type can be anything. Not so with all tools, not all tools allow you to do this. Okay, so it's your most universal tool. So a lot of engineering people that don't deal with oil and gas, but they deal more with environmental, like what's going on here, they still use a gamma ray tool just to get a basic idea of what type of rocks or sand or sediment that they're looking at. So let's look at that example. Okay, so I've shown this to some people before, they've seen it, but let's just get comfortable looking at some tools, right? So we're most interested in the left track, track 1, the lithology or correlation track. I have 3 types of tools on here, but the one I'm interested in is the big dashed line, the gamma ray, which is this one. Okay. So what's going on? Do you see any patterns here? What do you think this might mean based on what we talked about? Here's high gamma ray. Units, by the way, are called just API units, American Petroleum Institute units. So high radiation. Oops. Let me make it go back. Okay. So, high radiation, low radiation. What type of rocks do we have here in the hole? The big dashed lines represents the gamma ray tool. What can you tell me about the formation? There's a solid rock, 10,000 feet, so there's not any dirt here, it's solid rock. So what would you say, what type of rock do we have here compared to here? See, you start off with what you know. So what is the gamma ray log measure? Gamma radiation responding to those 3 elements, right? So the very first thing you'd say is that, well, I must have more potassium here and less potassium there. You don't want to just like jump to the conclusion, well, it's got to be this type of rock. First, just think about what is the tool actually measuring? Okay, don't think about the rock yet. What is it actually measuring? So this would be high potassium, low potassium. Now what would you do? What would be the next step? This is kind of cheating because you don't have the context. I'll tell you it's the Gulf of Mexico. Now you have some context. So what type of rock, if you had to guess, would have a high value of potassium, based on what we just talked about?
Shale.
Shales, right? Okay. And why are shales important in petroleum geology? Because they can form as seals. We're talking about a conventional reservoir system. They seal off the petroleum so it doesn't migrate. The shales are not very, what makes them seals? Not very permeable. They have a lot of porosity, can have a lot of porosity, but not much permeability, right? Sometimes you think of shales as not having porosity. They can have more porosity than anything. It's just not very useful or effective porosity, right? So this could be a seal right here. Or what type of rock? Let's go down to this one. What type is this thing? It has low potassium. It has a deflection or a kick to the left. Now, what do we say about a kick to the left means? You need to get some archetypal feeling here. A kick to the left means you have what? It's cleaner. It's maybe it's a reservoir, right? Remember from pattern recognition, you have to get this working in your head. A kick to the left is good. That means you have potentially a reservoir. Oh, but that's maybe going a bit too far. Well, how did I go too far by saying that's maybe a reservoir?
Because you haven't looked at everything yet.
Right? Well, all I've decided it has low potassium. Is that necessarily a reservoir? What if I had fused quartz? I don't know what fused quartz is, right? It's window glass, right? Well, what would that look like? Low potassium, silicon dioxide, nothing else. So that would look like this, maybe. Is that a good reservoir? Not exactly, it looks more like a seal. So you got to be careful, work step by step. So this, high potassium, low potassium. Okay, now if we know some context here, if we know that we're drilling through sands and shales, well, maybe it's okay to say, well, this might have some porosity, but you need to look at a porosity log, which we do not have yet. Okay. Now, just some of you will maybe be able to answer that, others will be unfamiliar. But the SP log is shown in the solid line. The SP log spontaneous potential is just looking at, a lot of them talking about it, but suffice to say, it's looking at the degree of potential difference, electrical potential difference between the borehole fluid and the formation fluid. When you have a big difference in potential, how do you get that? The big difference in electrical potential between measured in volts, or millivolts in this particular case. How do you get a big difference in voltage between what's in the borehole and what's in the formation? It's back kind of a high school or maybe grade school science experiment. How do you get a big difference in voltage? So you have ions that are moving to get a high voltage difference, right? So what type of rock are you going to have ions moving between the borehole fluid and the rock fluid? What type of rock does it have to be? What important physical parameter? How?
Is it permeable?
It has to be permeable, right? So maybe it's got to be a sandstone that's got porosity, but it also has to have permeability, right? So these SP logs are actually just showing, in a way, subject to lots of caveats, permeability differences. So you call this a very permeable rock, whereas this is less permeable, perhaps, because it has less of a potential difference. Potential difference shown here, kind of arbitrary units, they're millivolts, but the numbers are just relative. Okay. So, why do you think that you have kind of a suppressed SP log here, but you have an enhanced SP effect here? So that might mean high permeability. This could be lower permeability, but even that could be wrong. It could be wrong in that, well, what you're really talking about is a big potential difference. So what could actually suppress a potential difference between the borehole fluid and the fluids within the formation? Something that we're interested in, something that we'd like to find. What could you have in the formation fluid that would reduce the potential difference between the borehole and the formation? Something that we're interested in finding. Hydrocarbon, right? So if you have hydrocarbon in the formation, that could actually suppress the SP. That's what's actually happening here. Now this is electroresistivity, which we haven't quite explained fully yet, but this is showing high resistivity. So what do you think that represents? Highly resistive, relatively speaking. Again, these are orders of magnitude. So a little change is a lot, right? That's what logarithmic scale means, obviously. Okay. So high resistivity means that you have a conductor or an insulator. Insulator, and if you're just talking about a fluid effect, then this could be oil. Now what's going on down here? Is this also oil? Notice that the resistivity is initially high for the shallow. I know this is kind of asking to look at a lot at the same time. But shallow resistivity, it's only measuring this far to the side of the borehole, is fairly high. But what about the deeper? What about the deeper resistivity? It's fairly low. So can you get some intuition here? If I have high resistivity this far into the formation, but when I look this far, it's fairly low. What is that telling me?
We have some invasion. Or I guess it depends on what kind of fluid.
Right, we had a good spurt of low resistivity fluid,
Yeah.
but once we look deeper, excuse me, it had a good spurt of high resistivity fluid, but once we look deeper, then it's low. So if we have low resistivity deeper in the formation, what is that kind of fluid probably?
Water.
It's just salt water. So where did this come from? Where is this shallow resistivity come from? That's from the borehole. This was drilled with freshwater mud. You didn't know that initially, but it's drilled with freshwater mud. That freshwater mud spurts into the formation when you penetrate it. It's permeable, otherwise you wouldn't get a good SP log, and so that's where you get that effect. So I know that's kind of fast and a lot, but it points to the patterns that you get used to seeing. This is a typical oil pattern. Now the sandstone is not very well, it's not a very blocky sandstone. It's got sort of lots of shale, perhaps partings or laminations. Geologists sometimes call this a ratty sandstone. It's not a really good term. It's not fair to rats for one thing. But it suggests that you have lots of variation within the sandstone that's due to shale. Okay, so this could be oil. This is just salt water. So if you were an expert at looking at logs, you would immediately recognize this as oil. And this is like, well, yeah, you have a nice reservoir. Look at that deflection, very nice reservoir, but that's salt water. Okay, so just get some patterns going in there. And if I go over, just wave your arms and say, John, it's time to stop. Since I have a class at 4, I'm supposed to be at. Okay. So just kind of to summarize, your gamma ray log is showing you properties of the matrix. Okay, it's not influenced by the fluid, unless the fluid has high radioactivity, which is not likely. Okay, makes sense? So gamma ray log is just the matrix, usually, almost always, whereas your SP is responding mainly to the fluids between the borehole and the formation. Okay, for the logs we're looking at in the Decatur site, mainly going to be looking at gamma ray logs, but there's also some SP logs there as well. Okay, so estimate of plate content. So what you're really looking at with this deflection, this is high gamma ray, this is low gamma ray. This would be your shale baseline. So this is your maximum value. Okay, so you have sort of a consistent set of shales within your rock column. This could be your shale baseline, high potassium. But what you notice is that there's a deflection here, but not so much of a deflection here. So little changes in the deflection represent changes in shale content if you're in that type of environment, if you have sandy shale. Okay, so small variations just represent maybe clean versus shale. Notice that we're being careful. We're saying clean because it could be calcium carbonate making up the matrix, not necessarily sandstone. It depends on the environment. Okay. So the type of strat column a geologist would draw, geologists know this from birth, but typically a lines like this represent a shale. That's just what people draw. So it's supposed to make you think clay particles, I guess. I think that's how it's supposed to work. This is supposed to be sand dots, like little sand on the beach. And if you have both, then you'd say it's shaly, or sandy shale, or shaly sand. Okay, and then you're back to shale. So again, this would be called your shale baseline. So the first thing that you look at when you see a gamma ray log is, where is that shale baseline? So on the previous one, if I can go back, so here would be your shale baseline. Obviously, you need to have a lot of log to really find the shale baseline, right? So that's your shale baseline. I'm not having a feeling in my hands. There we go. Okay. And the way you could quantify this is with a simple equation that just says, well, I'm going to come up with an index value for how much shale do I actually have present. So the way I do that is I'll find my maximum deflection and call that clean. So that'll be a fairly low number, right? Maximum deflection be a fairly low number. I'll call that gamma ray clean. And then my gamma ray shale will be my maximum number, least deflection. If I can actually put numbers on it. So like this number would be what? 125, this would be maybe 25, something like that. So that represents my two numbers, my two end members. Then anything in between is going to be a number between 0 and 1. So perfectly shale, so this, the gamma ray index for this, if that's the maximum, would be 1. So this is very useful to give you an overall value of, if you're going to call this reservoir, you're going to call that seal, then you can actually get a number for your logs or pattern that shows how much sand versus shale. You can actually come up with a number. I have this much percentage of reservoir within this particular well log. I used to work for, like one of the companies I worked for, Shell Oil Company. One of my first jobs was, well, estimate the reservoir potential of this place based on this log. But how do I do that? Well, it's very simple. You just, which you do this with computers today, I had to do it by hand, is you just go and measure your gamma ray index. 1 is bad, or in other words, it's a seal, and 0 means you have 0 clay, it's all clean. Okay. So let's look at an example. This is actually a civil engineering example. I guess we're almost out of time. Go to quarter 2, right? Yeah. So I'll stop with this one. Okay. Just to show that engineers use this as well, not just petroleum people. This is looking at aquifers. Notice the depth is not very great, just down 500 feet. So maybe the water is still fresh, maybe, okay? So what's been done? They used a gamma ray tool to look at what? To look at good versus poor reservoir. How much, they want to have a drilling program. What's going to be the best reservoir for clean, drinkable water? So what did they do? Well, they just had a gamma ray log. You can see it goes back and forth. Same units as the last one, but that was petroleum setting. 0 to 150 API units. And then they just kind of arbitrarily sort of drew a line and says, well, anything to the left of this line is good reservoir, that's the dots, and anything to the right of the line is going to be a poor reservoir, right? And then that's their interpretation. So black means that's mostly shale or clay. In this case, it's probably clay because it's not consolidated. And anything that's lower gamma ray or higher deflection, we're going to call aquifer. Okay. Now, if this were a petroleum setting, what would control where you drew this line? If this is petroleum. What controls where this line is drawn? Because it just picks some place in the middle. It doesn't have to, I could draw it here, I could draw it here. What causes it to go this way? Something happening in the world. In the marketplace.
That's what.
Price of oil is going up or down if I move it this way. Yeah, right. So if the price of oil is low, then I want to get the cleanest formation possible. Okay, but the price of oil, if the price of oil is going up, then it's good to the last drop. I want to get every single little wiggle within here. Okay, so just an example of how you might use gamma ray to get reservoir versus non-reservoir. And I guess with that we'll stop. And so what we'll do on Thursday is finish the gamma ray logs and then move to the velocity logs. What I'll do with these PowerPoints, by the way, is I'll put them someplace where you can get them. I don't want to post them online because I'm violating probably copyright laws. I know that'd be the easiest thing to do. I'll make sure you get them. Okay, so it's not an exercise in furiously taking notes and never see the slides again. You'll have access to all the slides. All right, well, thanks for coming.